guys, you're welcome back to the channel Learn Maths. I hope you've all been doing great. Today we're going to be looking at the topic differential equations, right? So do well to like this video, subscribe to the channel and turn on your notification bell so you're going to get informed whenever we drop videos like this. Without further ado, let's go straight to the video. As we're going to be looking at the topics under differential equation. We're going to be looking at the types of differential equation, right? Now, how you're going to be classifying these types based on their order, right? The order of differential equation, the degree of these differential equations, and then we're going to be looking at the methods which you can use to solve these differential equation, right? We're going to solve basic examples. We're going to solve basic differential equation problem. Then on the subsequent videos, we're going to improve from there. So basically, we're all familiar with equations in mathematics. So what's the difference between the ordinary equations we know and differential equation? Now let's take a look at this example. This equation here, we have this equation y being equal to 3x squared plus 5x. Okay, now this is an equation, right? It's an expression that has the equal to sign. So if I'm to differentiate this quadratic equation, what am I going to get? Now the differential of this quadratic equation as dy dx is going to be 6x plus 5. Now this differential we've derived from this quadratic equation is actually a differential equation, because if you look closely, you're going to notice that we have a differential on the left hand side of the equation and we have some expressions at the other side of the equation. Then they are both connected with this equal to sign, right? Whenever there is this equal to sign, automatically that's an equation. You understand? So let's talk about the order of differential equations. Now if I differentiate once, the differential I'm going to get is going to be first order, right? We have first order. We're talking about the order now, the order of differential equations, right? We have first order, second order, third order, and so on, right? So if you differentiate a function for the first time, that's going to be the first order. Let's take another example, okay, similar to this, but let's make it of higher degree. So this is going to be 4x raised to power 3 plus, okay, 3x raised to power 2. Let's just work with this equation for now. Now this equation is cubic, no longer quadratic. You can see this was quadratic, but here the highest power or the degree of this equation is actually 3. The highest power there is 3, so it's cubic, not quadratic. Now if I'm to differentiate this the first time, that's dy dx, I'm going to get 12x squared, right, plus 6x. Now this is the first order differential of this function. I can go further to get the second order. I can go further to get the second order of this. That's going to be 24x, right? Okay, plus 6. Now this is second order. That's second order. If you want, you can go further to get the third order, right? And that's going to just be 24, right? 24 is the third order differential of this function here. You can of course get the fourth order if you want, and that's going to be 0. Okay, the fourth order is going to be 0, since the differential of this constant 24 is actually 0. All right, so before we proceed to degrees, before we proceed to talking about degree of differential equations, let's clear something up, because some people might be confused as to why we're having d square y over dx square. Why don't we just, or why are we having d cube y over dx cube? Get? Now why don't we just say dy square over dx square? You might be confusing yourself, like confusing this for this, right? You might be asking, why not this? Why this? Right? So now we're having dy square over dx square, which you feel, or some people might feel, is the way to go. Now, if you're to write this, if you're to express the second order this way, someone might also think that it is better to express this as dy dx all squared, right? Since you're having dy squared and you're having the x squared, why not just express it in this format, dy over dx squared? Now this is a totally different thing from what we're trying to say. What we're trying to say here is the second differential, the second order, right? Second order of differential. That's the message we're trying to pass, that this is the second order differential of this function. Now expressing this way is going to mean the first order differential squared, right? Now this first order differential we've got, this one here, if you square this, that's what you're trying to talk about here. That's what this expression is saying, that you should just square the first order differential, right? It doesn't mean this. This doesn't mean this, right? So this is the way, this is the standard, this is the way we're going to be expressing order differentials, right? So let's talk about degrees. Let's talk about degrees now. Okay, so if you're having an equation like this, let's just take this one. Let's take this one into consideration. You have the square y over the x squared equal to 24x plus 6. Now, if you observe closely, you will notice that this has the power of 1, right? The highest power here in this equation for the differential is actually 1. So this differential equation has degree of 1, right? Just degree of 1. But if you're asked of what the order is, like what's the order of this differential equation, it's actually 2, right? Because I can see the second order differential there. But if you're asked what the degree of this equation, it's going to just be first degree, degree 1, right? Okay, so let's see what degree 2 is going to look like. Okay, this equation here is actually of degree 2 because the highest power of the differential, I don't know the order if it's first, second, or third, but as far as the differential has a power of up to 2, then that's second degree, right? Second degree or degree 2. Okay, so let's just give more examples. Now we have this equation, this differential equation, dy dx raised to power 3 plus, okay, let's say the square y over the x square, okay, equal to it is an equation, so it has to have this equal to sign, equal to, let's say, 4, right? Any number. Now, this is first order. The differential here in this place is first order, right? But the degree of this is 3, third degree, right? Now, the differential here is second order, but the degree of this is 1. So I'm going to ask, what is the order of this differential equation and what is the degree? What's the degree of this same differential equation? Now the order, we're going to check what's the highest order you can find here. It's 2, right? Second order. So this is actually second order differential equation. All right. Now what's the degree? What's the highest power you can see here? This power of 1, this power of 3. So the highest power I'm seeing there is 3. So it's actually of degree 3. Do you understand the difference between order and degree now? It's quite different, all right? Don't get confused with the arrangement of the order, which might lead to you thinking it's the same way as expressing degrees. They're actually different things. They mean different things. All right. So let's look at types of differential equations. We just look at some types. All right. Let's look at some types of differential equations. All right. So a type of equation we should get familiar with is the homogeneous ones. The homogeneous equations, right? Now, when you hear the word homogeneous, what does it mean? The same, right? It's talking about something being the same, right? So let's take a look at this equation, y prime. Okay, before I proceed, let's explain this y prime stuff. Now, this function, I'm going to take into consideration the first equation we had, right? And the differential of this equation gave us this, right? I'm going to express this dy dx with this format. You see the function was y. You see the function was y and the y was differentiated, right? Okay. The function was y and y was differentiated. Now, instead of saying the differential of y is dy dx, instead of saying the differential of this y, that's our initial function, instead of saying the differential of y was dy dx, you can also express dy dx as y prime, right? You can express the differential of y as y prime instead of dy dx, right? So another way we can express the differential of y is f prime of x. This is f of x, which is actually the same thing as y. I believe we're all familiar with that term. This y here is f of x. That's a function of x, right? A function of x. Y functions or operates with x, right? If this was to be, let's say, y equal to 3u squared plus 5u. Now, y is going to be a function of u. That's f of u, right? A function of x, a function of u, or whatever you have here, whatever variables you have here. A function of the variables you have here, right? Now, this is a function of x, f of x. So this is actually y. What's the differential of this going to then be? The differential of this is going to be f prime of x, right? Since it's a function of x. All right, so I believe we're familiar or clear with that. So let's look at homogeneous equations. let's look at homogeneous equation. Now if I have an equation like this, y prime plus 4y, okay, let's say y prime prime plus 4y prime plus 5 equal to 0. I can say this is homogeneous, right? Because throughout this equation, I can only spot the differential of y, right? I can only spot the differential of y. Now let's give another example so we get familiar with this. Let's say we have, okay, 4y prime prime minus 3y prime plus y equal to 0. Is this still homogeneous? Yes, it's actually homogeneous because I can still spot just the differential of y and y itself. There is no other variable there like u, x, or any other variable, just y throughout the equation. So this is actually homogeneous, right? So let's look at the other type. Okay, that would be the opposite of homogeneous. Now that's non-homogeneous equation. Right, so what's this going to be like? Now you start seeing terms like x appearing in your differential equation. So let's give an example. We have 4y prime plus y equal to 3x squared plus, okay, let's say 5. Now this is no longer homogeneous because I can see y, I can spot y, its differential, and I can see another variable x appearing in the same equations, right? So these are basically the types of equations you'll be dealing with. These are basically the types of differential equations you'll be dealing with, right? Homogeneous and non-homogeneous. Homogeneous ones have a method you use to solve them, which is going to be quite different from the method you'll be using to solve non-homogeneous equations, all right? Now, some kind of differential equations you'll be meeting. We have the first order, the second, okay, we've discussed that. We've discussed order here, but we have methods we use to solve the first order differential equations and the methods we use to solve the second order differential equations. Alright, so let's list some methods you can use to solve the first order. For first order, methods like direct integration, right? Methods like direct integration is used. Okay, methods like separable variables can be used, right? Okay, other method, I think there is a method called integrating factor. Integrating factor method, right? Okay, there should be more methods for solving this first order differential equation. Right, let's look at direct integration. Now if you have a differential equation like this, y differential is equal to 4x plus 3. Basically what you're just going to do to solve this is integrate this directly. Just go straight to the integration part of the problem. I'm going to integrate this and I'm going to integrate 4x plus 3, right? I'm going to integrate the left hand side, also integrate the right hand side, right? So the integral of the differential of y is just going to lead us back to y, right? Now how about the integral of the right hand side? This is going to be, okay, so currently the power of x is 1. We're going to add 1 to that power, it becomes 2, and we divide with 2, right? And currently the power of x, which we can't see, is actually 0, right? Actually 0, that's why you can't see it. It's now as 1, x raised power 0. Alright, so I'm going to add 1 to the power of x, which is currently 0. If you add 1 to that, it becomes 1, right? So you divide it 1, nothing really changes. So y is going to be equal to 2x squared, okay, plus 3x. So this differential equation you are given, after solving it, you get the initial equation or the initial function that was differentiated to get this differential equation, right? And the method we use here was just direct integration, right? If you see a differential equation that you feel it can just be solved by integrating it directly, you use that method. Okay, there is no need to go around looking for a difficult method to use while solving a very simple problem. All right, so let's look at separable variables. Okay, before we proceed to separable ODE, separable variable, this is actually plus c, right? Whenever I integrate, you should not forget to add your constant plus c or plus k, depends on the letter you decide to use. Okay, so let's look at separable. This was direct integration, right, where you just see the differential equation and you integrate it directly to get your answer. Right, so let's look at separable ODE, or separable variable. All right, so separable variable, well, from the name, you're saying the word separable there, right? So basically there will be more than one type of variable there which you have to separate before you then proceed to solving the equation. Okay, let's look at this example under separable variable. This is dy dx equal to 2x, okay, let's say y plus 1. All right, so we are asked to solve this differential equation. Obviously this is a differential equation, right? But on this side now, on the right hand side, there is variable x and there is variable y. It's looking like it's not homogeneous, right, since there is a mixture of variables there. So if I'm to solve this using integration method, I'll have to separate these variables before proceeding with integration, right? So this is a fraction dy dx, this is also a fraction 2x over y plus 1. I'm going to cross multiply these fractions to see if anything changes, right? So y plus 1 is going to be multiplying dy, right? All right, then multiplying these other parts of the fractions, we're going to get 2x multiplying dx, right? Now y plus 1 is multiplying dy and 2x is multiplying dx. All right, so now we can actually proceed with the integration. I'm going to integrate y plus 1, right? I'm going to integrate y plus 1 with respect to y, since y is the variable there. And I'm also going to integrate the right hand side, that's 2x, with respect to x, since x is the variable there, right? All right, so now basically all you have to do is integrate both sides. All right, so the integral of y here with respect to y is going to be y raised to power 2 over 2. Currently the power of y there is 1. If you add 1 to that, it becomes 2, right? Then you divide with 2 plus this is 1, right? So you can say this is actually y raised to power 0. We're having 1 there, but it's actually the same thing as y raised to power 0, since anything raised to power 0 from indices is 1. So I'm going to add 1 to the power of y there now, which is 0. It's going to become 1, all right? And you divide with 1, nothing changes, equal to, all right, you should add k or c plus k or c, the constant, but I'm just going to be adding it on this other side. All right, so integrating this with respect to x, you're going to have, all right, this is 2x, currently having the power of 1. You add 1 to that, it becomes 2, and then you divide with that. Okay, I can add my plus k or c here now, right? So finally, we're going to arrive at y squared over 2 plus y is equal to x squared plus c. Okay, if you added c here and you added another c here, putting these constants together, you're still going to arrive at a constant. So basically, you should just add one constant, one letter, one c or one k. It represents all the possible constants that should have been there. All right, so this is the solution to this differential equation, right? So basically what we did, we separated these variables that were mixed and we proceeded to solving it with just the integration method. All right, so we're going to look at the integrating factor method next. All right, the integrating factor method, we're going to use this example. All right, okay, for the purpose of better understanding, maybe we'll use more than one example. We're going to use another, okay, dy over dx plus 5y equal to exponent of 2x, right? We just take these two examples for better understanding. So now what's the integrating factor method like? Let's solve this first one. Now here we have dy dx minus y equal to x, right? All right, so basically what we do here is we derive this integrating factor, right? We get an integrating factor, then we multiply the equation with it, like multiply every term in the equation with your integrating factor. Then after doing that, you just go straight to integration again, like we've been doing in other methods, right? Now, how do we get this integrating factor? How do we get this integrating factor? This is what you do. If you okay, before we get to that, if you look at these examples, you notice that we actually have mixed variables. We're having y and we're also having x. If it's possible for you to separate any of these, like apply separable ODE to this before integrating, that would be better, right? That would be preferable. But there is basically no way we can separate these variables and assign them the y, assign the other one the x. So we can integrate the first one with respect to y, integrate the other one with respect to x. There is no way we can actually separate these variables. So we have to make use of this method, integrating factor method. All right, so how do we get our integrating factor? How do we get our integrating factor? For this first example, how are we going to get integrating factor? Now, the y term, the term having y, right? Whatever the coefficient of y is, we're going to find the exponent of that, right? Okay, with x. Now, for this first equation, for this first differential equation, we have negative 1y, right? Now, this is negative y. That's the same thing as negative 1y. So, the coefficient of y there is negative 1, right? So, I'm going to have negative x, the exponent of negative x. That will be my integrating factor, all right? Same applies to this second one now. We have positive 5y there. So the coefficient of y there is 5. So my integrating factor is actually going to be the exponent of 5x, right? That's how we derive the integrating factor. Whatever the coefficient of your y term there is, you use it to get the exponent of x, and that will be your integrating factor. All right, so now we've gotten our integrating factor for this first differential equation. What do we do with it? What are we going to do with it? Okay, so this is what we do. I said you first find your integrating factor, then you multiply the equation with it. So I'm going to multiply through this equation with my integrating factor. This is going to be e, okay, exponent of negative x multiplying the y dx, right? And this is going to be negative exponent of x multiplying y. That's the second term, negative y multiplied by the integrating factor. And this is going to be equal to x multiplying the exponent of negative x, right? So what do we do from here? All right, so proceeding from here, we're going to integrate both sides, right? Now, this is the differential of y and e, right? This is the differential of y and negative e raised by negative x. The differential of y, also the differential of e raised by negative x, right? Now this middle term, which we're going to leave out for this next step, because it was the term we used to derive the integrating factor, right? We use this y term to derive the integrating factor, so there will be actually no need to include it in this next step. So I'm going to equate this to, okay, x that's equal to x raised by, okay, x exponential negative x. Okay, so I said we're going to integrate both sides now. Now the differential of this, if integrated, is still going to give you this, right? The differential of this, if integrated, is going to just get you back the initial term. All right, so how do we integrate this? We're going to integrate this using okay, integration by parts. Since we're having exponential function and polynomial function, two different functions multiplying each other, we're going to integrate this using integration by parts, right? Okay, so let me just give this here. This is x and this is e raised by negative x. That's exponent of negative x. All right, so how is this integration by parts? This is x, right? Now the differential of x is going to be 1, right? And the integral of e raised by negative x is going to be, okay, negative e raised by negative x, because that's actually e raised by negative x divided by negative 1, because the coefficient of x here is negative 1. You divide the negative 1, that's going to give you negative e, okay, negative exponential negative x. All right, so I'm going to multiply x with this, that's the integral of e, and then subtract with the integral of this multiplying this. All right, so let me explain what I mean. This is x multiplying negative e, right? So that's going to be negative, right? Negative x e negative x, right? If you multiply this is what you get. Now I'm going to subtract from this the integral of, now this multiplying this, all right? That's basically negative e raised by negative x, right? So to simplify this further, I'm going to say is negative x equal to, Alright, I'm going to say this negative x e raised by negative x. Now this negative, I'm going to factor it out, right? It becomes positive. I'm going to factor this out. Then I focus on the integral of e raised by negative x, right? I'm going to focus now on the integral of e raised by negative x, which I think we've done before. The integral of e raised by negative x is still going to give you negative e negative x, right? So I'm going to have here for this integral negative e negative x, right? And of course plus c or k. Now let's put everything in order. Let's arrange everything. All right, so this is y e negative x, and it's equal to negative x e negative x. Okay, this is going to be negative e negative x plus c. Now I'm going to divide through. I'm going to divide through with e negative x, right? E negative x, e negative x. So this cancels this cancels this cancels this. Okay, e negative x. All right, so our final answer is going to be y equal to negative x. Okay, what's this going to be? Negative 1. And this is going to be positive c over exponent of negative x, right? This is going to be the final answer for this. All right, so we're going to try the second example for better understanding. Let's try the second example. What's that? Okay, dy dx plus 5y equal to e, okay, exponential. All right, so how do we get our integrating factor? That's the first step, right? Get your integrating factor. Our integrating factor here is going to be e, right? The exponent of the coefficient of y. Now, the coefficient of y here happens to be 5, right? So this is going to be 5x. 5x. Previously, the coefficient of y was negative 1. That's negative 1 right there. So our integrating factor became e negative 1x, negative 1, negative 1x. Now this is 5x. We have gotten the integrating factor. That's step 1, right? Now what's the second step? You're going to multiply through the equation with this integrating factor. So I'm going to multiply this first term as dy dx. I'm going to multiply that with the exponent of 5x. That's the first term. Now for the second term, which we are not going to actually work with, we're going to multiply y, 5y rather, with the integrating factor as e 5x. And this is going to be equal to, you're also going to multiply this e 2x. You're going to multiply that with e, which is the integrating factor now, 5x, right? So what do we get? What do we get? Now this is the differential. We've done this before, right? The differential. This is the differential of y. This is the differential of y and the integrating factor, right? This is the differential of y and the integrating factor. Then this, which we are actually not going to work with, this is 5y, then the integrating factor equal to, this is e, exponent of 2x, this exponent of 2x. Now we're going to apply a little indicial law here, indices, right? This is 2x, this is 5x, the base is the same as e, right? We just add up the power. So this is going to be 5, 6, 7, 7x, right? A total of 7x. Okay, now that we've gotten to this point, what do we do next? The first step was getting integrating factor. The second step was multiplying through with that integrating factor. Now the next step is going to be integrating both sides, right? The left and right side, we're going to integrate both sides. All right, so I'm going to integrate the differential of y exponent 5x as this first term. Like I said, we won't be working with this because I'm not going to be integrating the integrating factor with the term I got the integrating factor with. So I'm just going to skip this and go straight to integrating the right hand side, right? That's the integral of 7x. Right, so what's the integral of the differential? The integral of the differential of this is basically just this term, right? There's no much logic there. The differential, the integral is just this. So that's going to be equal to, now what's the integral of e? Okay, integral of this is going to be the same thing, just with a fraction of 7, and plus, okay, k or c, plus k. Now to get the final equation, this is actually the answer, but we're just going to organize it in a proper manner. Right, so y is going to be equal to, and how do we do that? By dividing through with e5x. So y gets to be alone. Alright, so I'm going to divide this with this. You're going to be left with 2x, right? Still over 7. If you divide this term here with exponent of 5x, we're going to have 5x removed from 7x, leaving us with 2x, right? Then we also get to divide this term with the exponent of 5x. Okay, it's just going to be there because there is nothing to cancel out, right? So this is the answer for the second differential equation. Alright, so we're going to continue with second order differential. These are some methods we use in solving first order, right? Direct integration, separable variables, and integrating factor, right? Alright, so if you like our lesson so far, do it to like this video, subscribe to this channel, turn on the notification bell so you're going to be notified whenever we drop more videos like this. Also share this video to people out there, right? So they get informed and educated on these kind of videos, alright? And I'll see you guys in the next video where we continue with this topic.